Henrietta Swan Leavitt was born on the right day in a fitting place. July 4th, 1868, in Lancaster, Massachusetts. There must have been fireworks just outside the house, bright, pulsing, rhythmic. And behind those, far off and away, long before any sodium vapor or broadband LEDs could ruin your night sky, when Bortle 1 skies were the norm and not the exception, an entire sea of stars laid in wait for this newborn child to discover. Now, this was just 3 years after the American Civil War had ended, and in many ways, America itself was rebuilding and finding its path forward as a democracy. American astronomy, however, was still in its infancy, in terms of real-world impact anyway. At the time, America only had about a dozen observatories in operation. And among those, only 2 or 3 of them were doing actual professional grade research, and the rest were me and you. Among those institutions, however, were Harvard and the Harvard Observatory. Europe was handily beating America in all things astronomical at the time. So, on July 4th, 1868, you could say it was a fitting day for someone who was instrumental in the independence of freedom for early women's rights to work in a field that was not very friendly to women at the time to be born in America. Born to a conservative mother and father, Henrietta's dad, George Roswell Leavitt, was a local minister who moved the family around quite a bit until finding his own flock. Eventually, they would settle in Cambridge, Massachusetts. Now, Henrietta loved her father, but she was named after her mother, Henrietta Swan Kendrick. Also of note, her dad, and therefore her, were descendants of one Deacon John Leavitt, an English Puritan tailor who had helped settle Massachusetts back in the early 17th century. Back then, astronomers would often have to tell horoscopes to fund their research.
Yes. Interesting. The Knight of Cups and Page of Wands. This means you shall intern at Hogwarts, fetching coffee for wizards. Also, were you aware there will soon be a lunar eclipse? Please give me money. My wife, she wants new shoes.
You see, the Ptolemaic model and way of thinking was still going strong, and many folks believed that the Earth was the very center of the universe. The Copernican revolution would not be televised, so it seemed, because books took decades to spread. And even though Copernicus had published De Revolutionibus Orbum Celestium, or On the Revolution of Heavenly Spheres, in 1543, by the early 1600s, saying the Earth wasn't the center of the universe could still get you killed in some circles. And while 200 years later, Henrietta would not have to worry about being hung for saying Earth revolved around the sun, she would certainly face her own unique challenges. Ironically, as a young girl, Henrietta didn't take much of an interest in the stars, no more than the average person anyway. Whereas someone like Galileo Galilei knew from a very early age as a little boy sitting under Bortle 1 skies in Pisa, Italy, that he wanted to know everything that he ever possibly could about the stars. Or Carl Sagan, who famously, quote, devoured every science fiction and astronomy book he could get his hands on as a child.
Asked the librarian for a book on stars. She gave me a funny kind of picture book with portraits of men and women with names like Veronica Lake and Alan Ladd. I explained that wasn't what I wanted at all. And for some reason then obscure to me, she smiled and got me another book, the right kind of book. I was so excited to know the answer that I opened the book breathlessly right there in the library. And the book said something astonishing, a very big thought. Stars, it said, were suns, but very far away. The sun was a star, but close up.
No, Henrietta had a fairly typical conservative Christian upbringing. It wasn't until she was in her late teens, at age 17 specifically, that things started changing for her. For starters, Henrietta had always lived at home and been very close with her mom and dad and family. She was devoutly faithful as a young woman and stayed that way for her entire life. Having been raised by her father and as part of the congregation, she couldn't imagine being without her family. Worse still, in the 1880s, it was incredibly rare for a woman to attend college, let alone a prestigious one. But Henrietta had big goals and big dreams, and therefore big choices to make. She just wasn't really sure what those were quite yet. It's like when you wake up in the morning and you know you've had a very peculiar, very distinct dream, and yet you can't seem to remember it. It eventually comes to you, but usually it's when you least expect it. So, this was Henrietta's dilemma. She knew she wanted higher education, but we were still roughly 40 years away from the women's suffrage movement passing. And like I said earlier, getting into a prestigious university as a woman at this time in America was nearly unheard of. Even just getting into a regular college to earn a degree was incredibly rare, as most colleges didn't even offer courses for women. Being in Cambridge, Henrietta knew Harvard was one of, if not the most important and prestigious universities that there was. But Harvard was a boys' club. So she had to turn her eyes elsewhere. Elsewhere ended up being west. 700 miles west, to be precise. So, Henrietta made the incredibly tough but remarkably brave decision to leave home at a very young age by herself so she could attend a revolutionary college that was far ahead of its time. She packed her bags and hopped on the local horse car, or horse-drawn tram. An early form of public transit, the horse car was very much like the modern trams of today, on steel railways that take passengers by the dozens to different areas of town, with one key difference. Instead of electric or gas engines, they were pulled by horses. A single horse car could work with 5 or 6 horses for 5 to 6 hours a day and pull for over a dozen miles. Eventually, with the advent of streetcars with electrical power through pantographs, the horse-drawn tram would be phased out. But on this particular day, in this particular year, Henrietta Leavitt traveled by horse car as she made her way to Boston. Upon her arrival at Union Station, she could hear the clatter of hooves on cobblestones and smell the bitter coal smoke in the air and feel the cool fall weather beginning to take hold. Now you have to understand, Union Station in Boston in the 1880s is not the same as Union Station of today. It was a huge, sprawling, labyrinthine complex built to handle an explosion of rail travel powered by the steam age. Now, imagine that you are Henrietta stepping off of that horse car. The driver hoists down your trunk and hands it to a station porter whose sleeves are rolled up and smells faintly of coal dust. He then manhandles it onto an iron-wheeled hand truck. Henrietta, watching all of this unfolds, keeps only her handbag close as the trunk with all of her worldly possessions vanishes behind swinging doors, tagged and bound for the baggage car. She heads for the gates, entering the massive complex through an archway standing some 5 stories tall, eerily reminiscent of Paris's Arc de Triomphe. The Victorian styling is everywhere, and she admires the building while also paying close attention to those around her. Her uncle warned her not to stare too much at any one thing, as it's an easy way for the con men to pick you out of a crowd. With thousands of people coming and going every single day, the opportunity at Union Station for easy money is just too tempting for some. Pickpockets are everywhere. Drunkards stumble about. Con men loiter, offering their scam change schemes and rip-off portering services. Henrietta clutches her purse closely to her chest, takes a deep breath, and begins walking towards her coach. When she finally arrives and finds her seat, after handing over her ticket to the porter, she closes her eyes and asks herself, am I making the right choice? Have I lost my mind? Traveling alone, so very far away, all in the pursuit of what? What will I study? What excites me? What if nothing does? What if I'm a failure? What if? What if? What if I can change the world? The wheels begin to turn, both physically and metaphorically. Oberlin College is a private liberal arts college and conservatory of music located in Oberlin, Ohio, just 10 miles south of Lake Erie and about 100 miles north of the capital, Columbus, Ohio. Founded in 1833, Oberlin is the oldest co-educational liberal arts college in America, which was, without a doubt, the best place for our hero to land. You see, co-educational is long for, of course, co-ed, which meant both men and women could attend the college, which was not a normal practice back in 1833, and in fact, still quite rare in 1886, which would have been right around the time a 17-year-old Henrietta made her train ride 700 miles west to Oberlin. Just pause on that for a moment and think about it. It's the late 19th century. You are a young 17-year-old woman. The country is still nearly 40 years away from women even voting, and you're traveling by yourself over 700 miles away from home and your family that has been by your side through thick and thin. And you're doing it all by yourself. It must have been terrifying. How much easier would it have been if Henrietta just said, you know what? I'm gonna chip in at the church, find a man, and get married. I really don't need a higher education. A man can take care of me. I'll just have some kids, settle down, and start my life in my family's footsteps. Only 2 to 3% of the college-age population even went to college by the year 1900. And of that, only 1 in 5 were women. So yeah, it would have been much, much easier, and statistically speaking, much more likely for Henrietta Swan Leavitt to just stay at home and start a family. Instead, she started classes. She took a wide array of them, not yet sure exactly what she was looking for. She studied Latin, Greek, the fine arts, philosophy, while also pursuing more pragmatic studies, such as analytic geometry and calculus. She didn't know it at the time, but those rather boring math classes were the very same skills that would help her change the astronomical world from the ground up. George Johnson, a biographer, wrote of Henrietta. Her colleagues saw her as quiet, meticulous, and persistent. She worked hard and she never complained, even though women's contributions were often downplayed to give men more credit than they deserved on any given project. She worked to further science and to help her understand the world better. She didn't care what men thought about her or her work. Sadly, we don't have too many records of these early days at Oberlin of Henrietta. That said, when she closed that chapter after 2 years of studies and turned the page, well, that's when things started to get very interesting indeed. Henrietta seemed to truly come into her own after transferring to Radcliffe College after 2 years of studies at Oberlin. To her family's absolute delight, she was able to move back closer to home than ever after being accepted to Radcliffe. But let me slow down. Back then, it wasn't known as Radcliffe College. You see, the quote, Harvard Annex was formed in 1879 by prolonged efforts of a particular group of women who wanted to be allowed entry into Harvard. One Arthur Gilman, a local resident of Cambridge, Massachusetts, who was a banker, writer, and philanthropist, ended up founding the Annex, later known as Radcliffe. At a time when higher education for women was a fiercely debated and highly controversial topic, Gilman only saw education as an opportunity that should be available for everyone. Also, he knew that he wanted his own daughter, Agatha Gilman, to have an opportunity to be taught by the best professors in America. He founded the Annex and became an executive board member, paving the way for women like his daughter and our hero to attend. So Henrietta enrolls at Oberlin College at 17 and transfers to Radcliffe 2 years later, which was then also known as the Society for Collegiate Instruction of Women in Cambridge. But you know what? For simplicity's sake, let's just call it Harvard from now on, because it would eventually merge as part of the official school. What would normally have been a simple 4-year degree, though, unfortunately took much longer due to illness that Henrietta had to endure throughout her college years. Now, let's take a moment and pause on this. As I said earlier, there's unfortunately not a lot of info about Henrietta in the world. In putting this story together, I've scoured countless resources, looking for the thread of humanity throughout the life. And here's where I think so many of them seem to fall short. Imagine for a moment that you're a 19-year-old girl who's doing something so far removed from what is considered normal for her family and, yes, society. You've already traveled 700 miles from home by yourself and then returned to attend an even more prestigious university and continue your studies, only to have your dreams and goals delayed by illness. It would have been so easy for Henrietta to give up. No one, I mean no one, would have blamed her if she dropped out and moved back home with her parents. She was sick. She couldn't even make it to classes most days. It took her 7, nearly 8 years to complete a 4-year bachelor's degree. And it was not because she was out partying. We'll touch on this a little bit more later, but suffice to say, she was brave, very brave, in pressing forward despite all the odds being stacked against her, including her own health. When she transferred to Harvard, Henrietta continued to study a broad range of topics. Even still, up to her junior year of earning her bachelor's degree, she had not taken a single astronomy class. Entering her senior year, Henrietta saw a posting for one of the two astronomy classes that were being offered at Radcliffe at the time. Astronomy 1, Theory. This was the classroom class, the place where you read about the actual why behind it all. You learned celestial mechanics, the motions of the planets, Kepler's law, Newton's law of gravitation. This is where Henrietta's prior learning in calculus and other arithmetic courses she had taken earlier in her career would truly help her understand the bigger picture. This is also when she became completely enamored with the stars. Not only was she absolutely fascinated by the night sky, she was also very good with numbers. You see, to understand the universe is to understand math. Without a solid understanding of the equations that describe the fundamental laws of physics, you can't truly grasp the way the universe works. Now, this is also at a time when she was beginning to have more stomach issues and having to excuse herself from classrooms for not so fun trips to the restroom. But she persisted, continuing her journey, learning about spherical astronomy and how we develop maps for the skies. She learned about right ascension and declination, and began to grasp how astronomers were able to track these heavenly bodies so accurately year after year. And there were textbooks, of course. Simon Newcomb's Popular Astronomy, published in 1878, was on the reading curriculum at the time. Newcomb, a Nova Scotian-born polymath who attended Johns Hopkins University, was inspired himself early on by Sir Isaac Newton's Principia, written in 1687. He was instrumental in work toward calculating the speed of light, planetary motions, and even discovered Benford's law, a principle that observed that in any list of numbers that have an arbitrary set of data, more numbers will tend to begin with the number 1 than any other digit. It's true, try it yourself. It was with this info from these people in this place that Henrietta found her true calling, eventually passing her astronomy theory class with an A, though some records do show it was an A-. So she graduates at age 24 from Radcliffe College, again, Harvard College, with a bachelor's degree, and takes another astronomy course under Edward Charles Pickering, the director of Harvard's observatory. She begins to narrow her field of focus as most astronomers do, finding that her interest lies in stellar photometry, which in layman's terms means measuring the brightness of stars. In order to pursue her passion, Henrietta gets a position working as an unpaid volunteer assistant under Pickering, the director, cataloging stars from the observatory's countless photographic plates. Now, Pickering was quite the character in his own right. Born to a family of astronomers local to Boston, Edward had built his own telescope by the age of 12. He was an avid climber and cyclist, and actually discovered the first spectroscopic binary stars, which he describes in Elements of Physical Manipulations, written in 1876. Essentially, this method was a way of observing the Doppler shift of a star's spectral lines to detect an unseen second or binary star in the system. To this day, this method is still used to detect binaries that cannot be visually resolved with even the best telescopes. One of my personal favorite stories about Pickering and why he loved women working in astronomy was he had apparently become quite fed up with his male assistant's sloppy cataloging of stars, firing him one day while commenting, "Even my maid could do a better job than you." And in fact, he put his money where his mouth was, hiring his personal maid, Williamina Fleming, as his first female computer on staff. Fleming, who did phenomenal work over the years, was actually the first person to discover the famed Horsehead Nebula. We could tell an entire story on Miss Fleming and Mr. Pickering as individuals, but those are stories for another day. It was under Edward Pickering that Henrietta would enter into a workroom each day lined with desks that were piled high with photographic plates, each filled with negative images of stars
waiting to be cataloged.
Speaking of photographic plates, this was a time before printing photos of stars was an option. But human ingenuity always finds a way, and it surely did with astronomy. Photographic plates were the mirrorless sensors of the 19th century. Incredibly delicate and fragile pieces of rectangular glass, often measuring just 1 millimeter in thickness. They had truly revolutionized astronomy. To make a photographic plate, a clear, rectangular piece of glass, usually around 4 by 5 inches, was meticulously cleaned and polished by hand to ensure that there wasn't so much as a single speck of dust or a smidge of oil that could damage the exposure. Then, a thin coating of gelatin mixed with silver halide crystals was spread evenly over the surface of the plate. Luckily for Henrietta, by her time, the Kodak Corporation had begun producing these plates by machine, which had made dealing with them much easier. Prior to Kodak's mass production, these plates had to be made on-site at the observatory using a different substance, and the astronomer only had minutes to place the photographic plate into the telescope before it would start exposing. The thin plates were removed from a light-proof box that they were shipped in and placed into a rectangular clamp in front of the telescope's focal plane. A photon is born in the core of a star, which is eventually shaken loose by nuclear forces working over millions of years. It ricochets through the star's plasma, bouncing around like a kid in a bouncy castle, oftentimes for eons, before finally being ejected from the stars and slipping free into interstellar space. Once free, it begins to race across the void, the fastest anything in the entire universe. The photon, traveling at 299,792 kilometers per second, it travels for thousands of years, maybe millions, through a seemingly never-ending dark emptiness, dodging nebulae, skirting past galaxies, never, ever slowing down. Finally, it paints a metaphorical crosshair after millennia on your telescope. The photon gracefully blasts through Earth's atmosphere, where it encounters its first challenge: nitrogen, oxygen, aerosols, dust in the sky, trying to scatter its light. But it endures, traveling to the glass. Finally, it reaches the objective lens, if it's a refractor, or mirror if it's a reflector. Along the way, man-made curves and coatings engineered with absurd precision guide the light with unbelievable precision. Passing through each piece of glass, the light slows ever so slightly as light travels slower in glass than in a vacuum, and then speeds back up as it exits and reaches the promised land, the focal plane. It is in this place that the photon joins all of its millennia-traveling brothers and sisters and reunites to converge upon the photographic plate, or, if we're back in modern times, your mirrorless sensor. All those photons entered the objective lens of the telescope and hit the plate where the gelatin and silver halide mixture waits. Some silver halide grains would begin to form a latent image when they are struck by the photons, which would later be developed in a darkroom with chemicals that reduce those altered grains to a metallic silver. The silver darkens, leaving behind tiny black dots where light had struck. A chemical bath is then given to the entire image, which washes away the unused halides so the image will not fade in daylight viewing. And what remains is a durable negative image of the stars, nebulae, or galaxies that were captured through those very same photons that entered the telescope. When you take a photo of the stars, you are truly capturing the essence of time. One immediate huge advantage that using photographic plates had was that astronomers were finally able to see longer than the time that the human eye could provide, which was just tenths of a second, depending on how well adjusted to the dark the eye was at any given time. By allowing the plate to be exposed for long periods of time to light, and manually tracking the star by keeping it centered while looking through a guide scope and feathering right ascension and declination knobs, astronomers could capture long-form exposures of the universe. These hours-long sessions were both physically and mentally brutal. If you happen to lose track of where you were manually keeping your telescope centered on the crosshair of the guiding telescope for even just a few moments, the image would be blurred and therefore ruined. Since these telescopes were massive, usually high f-stop instruments which everyone wanted time on, it was absolutely critical that an error was not made while guiding. Edward Emerson Barnard of Barnard's star fame, which is the second nearest star to the Sun, trailing only behind Alpha Centauri, was one of the early prolific users of photographic plates. Barnard was the definition of pioneer in the field of astrophotography, collecting some 370 dark nebulae in the Barnard Catalog of Dark Markings in the Sky, usually just referred to as the Barnard Catalog, which can still be found in Nina, Stellarium, and countless other planetarium applications not named ASI Air. Now, after the plates were exposed and developed into a viewable photograph on glass, they could be clamped back into the telescope in front of the eyepiece, which could then be used to line the stars up in the exact same orientation as what was on the plate, thus recording the exact position of the stars in the night sky. The astronomer could then make note of the right ascension and declination coordinates on the wheels of the telescope mount, and they would know exactly where they were looking in the night sky. They completely solved the problem of not being able to precisely record where the stars were and share those exact locations while being able to verify it with certainty. This may seem simple to us now, even elementary, but at the time, this was monumental. In fact, it's so important we still refer to it pretty much every single day to this day. You do yourself, in fact. After all, I'm sure you've plate solved an image recently, haven't you? So, it's 1893, and Henrietta is volunteering as a human computer at the Harvard College Observatory. I know that might sound strange, but human computers were actually a very real and important thing. Back then, we didn't have real computers to do the complex calculations that were required for astronomical equations to be solved. So it was incumbent upon those who knew and understood the math to work it out. Sadly, also, women weren't allowed to do the actual observing at the observatories. Looking through the eyepiece was reserved for the men alone. Ironically, the things that were supposedly more suited for women, such as the detail-oriented task and the assistant-type work, things like measuring the photographic plates, cataloging stars, and doing the actual math, was truly the work that required the most extraordinary patience and work ethic. It was, in short, the work that truly mattered. Pickering knew this inherently, and while it wasn't the only reason that his workforce of computers was full of females, it was definitely a big one. He pretty quickly found out that women were much better suited to tasks that required actual patience, having dealt with sexism throughout their entire careers. He was likely onto something. Anyone could look through an eyepiece. Not anyone could solve the type of equations that Henrietta and the other ladies were tasked with as human computers, day after day and night after night. Sadly, it was also during this time when Henrietta's hearing began to fail her. Though it was a slow and somewhat arduous process, Henrietta would eventually lose all hearing in her 20s, becoming deaf. While we don't know exactly what caused her hearing loss, we do know that scarlet fever and the measles were both extremely common in the late 19th century and could often cause hearing loss when they damaged the inner ear. Another distinct possibility was meningitis, which, thanks to science, has since been decimated worldwide by as much as 99% after routine influenza vaccines became common in the 1980s. The same can be said for scarlet fever and the measles. Both have been mostly eradicated in first world countries thanks to advances in medical science like antibiotics and the MMR vaccine that weren't around in Henrietta's day. Sadly, none of our population that lives today knows firsthand the horrors that were experienced in the 19th century and also those who came before them. But if current trends continue, that may very well change. By the age of 30, due to growing health issues, Henrietta was sadly forced to return home. She packed up her bags in Cambridge and headed back inland for home in Lancaster, Massachusetts. During this time, we don't know a lot about what Henrietta went through. We can imagine that there were countless nights where she'd go outside and look up to the thousands of stars which she had endlessly cataloged for years, and dreamed of one day returning to the Harvard Observatory to continue her work and studies. Luckily for us, she never cut ties with the observatory, staying in communication via correspondence with all of her colleagues and Edward Pickering over the years. As Henrietta approached her mid-30s, her health finally stabilized, though her hearing was now fully gone. Not being one to let a disability prevent her from moving forward, Henrietta reached back out to Edward Pickering with the great news that her health had gotten well enough to return to work at the observatory, if he would have her. Not only would he have her, but as it turns out, he wanted to formally hire Henrietta as a paid staff member. Remember, up until this point, Henrietta had only done volunteer work for the observatory. Now, that being said, she wasn't making a fortune. One of the sad truths was Edward Pickering had also hired women because he knew men would never do the work that they were doing for the pay that he was willing to offer, 25 cents an hour. This was typically less than what an average secretary made at the time, and obviously required a tremendous deal of more skill and patience, with the ability to work quietly in solitude for hours upon hours of time, studying plate after plate of stars. Luckily for our hero, this was right in her wheelhouse. Losing her hearing had only helped sharpen her eyesight, and she was always quiet to begin with, so the job still just made sense for her. Said colleague and fellow Harvard astronomer Solon Bailey in 1922. Miss Leavitt was always of an especially quiet and retiring nature, always absorbed in her work to an unusual degree. She had the highest esteem of all of her associates at the Harvard Observatory, and her work was carried out with unusual originality, skill, and patience. So yeah, you could say that Henrietta had definitely found her calling. In doing so, she began making discoveries. That being said, she never let her ego take hold of what's important, nor would she ever let go of that core love for astronomy. Once, a census worker was visiting Cambridge and happened to knock on her door and ask her occupation. Henrietta simply replied, "I am an astronomer." So, Henrietta worked 9 years for free as an apprentice. She worked through sickness and health and still somehow managed to continue her journey. Illness, losing her hearing, systemic sexism. Most of us wouldn't go 2 weeks without a paycheck. Imagine going 9 years because you're doing something that you love so much while enduring that kind of pain. She was finally rewarded 9 years after graduating with a paid position. At age 34, Henrietta is assigned to work on variable stars in the southern hemisphere. Stars that she would never even see with her own eyes. There is a quote that is often second-handedly attributed to another computer from Harvard Observatory, Annie Jump Cannon. It says, "How she loved the clouds," referring, of course, to the Magellanic Clouds, both large and small. They were her favorite. They were also clouds that Henrietta would never get to see with her own 2 eyes. Harvard famously housed, and still houses, though it is now retired, the Great Refractor, a 15-inch aperture behemoth, the biggest in all of America for over 20 years when it had its first light in 1843, and it was one of the world's most powerful telescopes. A young physicist named Edward Pickering had set out on a goal of cataloging each and every star in the entire night sky. By the time they finished, Harvard had cataloged nearly 45,000 of them. But Henrietta would not work on these stars, these northern stars, gathered with the Great Refractor. For she was tasked with studying the southern skies that held the Great Magellanic Clouds. Clouds that might have been best seen from some nights from the mountains of Peru, where Harvard Observatory's Arequipe station resides. One Swan Bailey is working. He is hot. The air is thin. The Milky Way stretches overhead, and Orion is jumping in the northern skies, upside down. Strange creatures mark every bit of the night sky and are unlike anything in Cambridge. Whales, giant boats, chameleons and toucans. Strange sights indeed. Solon thinks to himself, David Crosby was right. He understood exactly why he came this way. But those clouds, he says to himself as the telescope peers into the abyss. Thousands of miles away, in a dark office on a snowy night in Cambridge, Massachusetts, a small box hums with a fluorescent glow on a single tidy desk in a room crowded by piles and piles of glass. Gracefully, a woman quietly studies the features. Those clouds, she silently thinks to herself, with a hint of wonder in her thoughts, while lifting a magnifying loupe to her eye. The box continues to glow. Back now in the mountains of Peru, Bailey's sweat is paying off. He has steadily tracked a single star in the small Magellanic Cloud for over 2 hours on this night, which should provide a very nice image to send back home. If only the 1 millimeter thin plate of glass can survive the journey from the telescope to the case, which was padded with sawdust and straw, followed by a short jaunt to the truck, then a long, very long and bumpy ride to the docks, followed by countless ports of call as they made their way up the Pacific coast before ending up on a railway somewhere in California, hopefully to travel a few thousand more miles safely back to Henrietta and the other waiting computers to be studied. Solon Bailey laughs to himself and closes the case. For Henrietta, the wheels are turning fast. She is firing on all cylinders now. Billions of neurons in her brain are passing electrical impulses across synapses. The circuits light up like a well-conducted symphony as she begins to grasp the magnitude, pun intended, of what she's seeing. And surely this is of the first magnitude. Her heart rate quickens and her palms feel a bit clammy. The room is still quiet, but for the hum in the box that is backlighting the plate, showing thousands of stars in the small Magellanic Cloud that Henrietta has been staring at all night. That and the sound of her pencil quickly etching the notebook that sits beside her on the desk as she calculates and then confirms her findings. The photons that left those stars all that time ago, that traveled for millennia to reach Peru. Solon Bailey traveled from Cambridge, Massachusetts to Peru to reach the light. The plates had traveled for months to reach Cambridge, and in that quiet room, Henrietta Leavitt would turn those very same photons into law, all while cementing herself as one of the greatest minds, one of the bravest, most persistent, most unstoppable male or female astronomers to ever grace the human race. Period. How she did it? Well, that was as brilliant as those southern stars that Solon got to see in Peru. Henrietta had long been fascinated with variable stars. These are the stars which change in brightness over time. Studying the brightness of the stars that were scientifically measured in the exact same way as is befitting the scientific method, she noticed that some of the stars have brightness that goes up and down over a period of time that was always the same and always repeating. It was like the star was breathing. Its outer layers would quite literally expand and cool, and then contract and heat back up. When the stars would grow in size, again, they would cool, and then they would contract and heat back up. The temperature swing would essentially determine how bright the star appeared to us from Earth. But all variable stars are not created equal. There are many different flavors. Cepheids, which have periods between 1 and 100 days, RR Lyrae, which are much shorter and faster, only a few hours to a day, and Mirror-type variables, which could cycle for as much as 1,000 days, sometimes even longer. Now, to understand the problem that Henrietta was solving, first you have to understand how astronomers came to appreciate the distances of the planets and the stars. Copernicus had put the sun in the center of our solar system before his death in 1543, in the Copernican Revolution. Johannes Kepler flattened the proverbial planes by putting ellipses in motion. In an era which made no distinctions between astronomy and astrology, Galileo Galilei gave us the telescope and the eyes to see the stars and wanderers or planetas through them. Isaac Newton theorized gravity and the laws of motion and helped us further refine the scientific method and enter the Age of Enlightenment as we began to ask the questions that would be left for those who followed in their footsteps. And though large footsteps those may have been, if I have seen farther than others, it is because I stood on the shoulders of giants, Newton once said. In that dark office, Henrietta Swan Leavitt stood tall on the giantest of shoulders. So, here was our problem. Try this. Hold your hand out at arm's length in front of your face and make a fist. Now, raise one finger, your pointer finger. Now, close one of your eyes. Okay, ready? Switch eyes. Blink back and forth between your two eyes, always keeping one closed. It's something nearly all of us did as kids at one point and were completely awed with. But this effect is nothing magical. It is the optical illusion known as parallax. Early astronomers, including Galileo, realized you could use parallax to measure great distances of stars in the night sky. How? Well, instead of using your left eye and right eye, you would use July and December. Instead of using your finger, you would use a star. You see, if you pick a star in the night sky and measure it from the opposite ends of the solar system and mix in a little trigonometry, you can see the position of all the stars in the background of that same star shift ever so slightly, just like your finger does. The only problem is, these stars would only appear to shift for about an arc second at most. This was useful for measuring nearby stars, But anything that was further away quickly became impossible for 19th century telescopes, and still is to this day. The telescopes of the 19th century were not able to make such demanding calculations with any statistical certainty. In short, they could tell that it worked and even have success in many cases. It just didn't work well enough to be useful in most cases. Another standard yardstick would need to be found. Henrietta, who had studied variable stars for her entire career, began looking through plates of photos from the Harvard Observatory in Peru that arrived recently, and was studying those of the Small Magellanic Cloud. On these plates, she noticed something. Some of these stars appeared to be pulsing in brightness. She started plotting out lines of which stars were pulsing and for how long. Since all of these stars were located within the Small Magellanic Cloud, she could be reasonably sure that they were essentially the same distance from Earth. That meant that any difference in their apparent brightness was due to their intrinsic or actual brightness, not because of their distance. She realized something. The brighter stars actually pulsed slower, and the dimmer stars appeared to pulse faster. What this meant was that she could now tell which star was brighter just by knowing its period. And since she could map out any star's period over any course of time and determine the time at which it reached its absolute brightness, she could then compare that with its apparent brightness from Earth, and using some simple math, calculate the distance modulus. Put simply, if you see two stars in the night sky and they appear to be about the same brightness to you here on Earth, you can use a telescope and track them night after night, cataloging them both from their dimmest points to their brightest points and back again. This is known as a light curve. If one star reaches its brightest point in 10 days and the other takes 100 days, the star that takes 100 days, even though it appears to be the same brightness in our night sky, is actually much, much further away. This is what Henrietta discovered in that dark office, and this is what became known as Leavitt's Law. The real stroke of genius on Henrietta's part came specifically from using the Small Magellanic Cloud, because she knew all those stars had to be close together. Therefore, their brightness had to relate to their actual intrinsic power, not their relative distance from us. From that point, it was just a matter of plotting out periods versus brightness and having results confirmed time and time again. Henrietta made her period luminosity relation discovery between 1908 and 1912, but never really got the chance to use it herself. But unlike some discoveries, this one would not take long to bear enormous fruit. Throughout the 1910s, Harlow Shapley, another hire of Edward Charles Pickering at the Harvard Observatory, used Henrietta Leavitt's period luminosity relation to measure distance to globular clusters within the Milky Way. Over time, this eventually let him work out an estimate of the true size of our own Milky Way galaxy. which was indeed much larger than anyone before him had anticipated. It also proved, beyond the shadow of a doubt, that the sun was never at the center of the Milky Way, which, somewhat incredibly, was still unknown in 1910 when this major shift took hold. So, Leavitt made the measuring stick and Shapley laid it across the Milky Way. Before this, nearly all astronomers agreed the Milky Way had to be a relatively modest few thousand light years across at most. It was assumed to be a pancake of stars with our sun in the middle. Shapley estimated that the Milky Way was actually closer to 300,000 light years across, though later, in reality, we would concede the number to be a bit too ambitious, with the actual size lying somewhere between 100 and 200,000 light years across. Still, it was massively larger than anything anyone before him could have ever predicted in their wildest dreams, and Leavitt is the reason why. She was the reason why we no longer believe the sun was at the center of the Milky Way when you get down to brass tacks. Shapley would continue his work at Harvard until 1921, when he left Harvard to join the Mount Wilson Observatory, before later returning to Harvard to become the director of the observatory himself. Now, shortly after that, in the early 1920s, a man named Edwin Hubble came along with his own massive ambitions. And with a few tweaks of Leavitt's law, along with the help of a 100-inch telescope on Mount Wilson, Hubble began taking photos of the Andromeda galaxy. He plotted the light curves, just like Henrietta had in the Small Magellanic Cloud, to get accurate periods and find their absolute magnitude or intrinsic brightness. He then compared that value with their apparent brightness. Remember how bright the star appears to be, regardless of the size or distance to us on Earth, and was able to calculate a distance that is so very distant from anything we had seen inside the Milky Way that he was certain the so-called Andromeda Nebula was not a nebula at all. No, M31 was a completely different galaxy, and now we knew exactly how far it was from our own home in the Milky Way. Henrietta Swan Leavitt worked quietly, usually alone in a dark room by herself for hours at a time. She didn't earn much. She never sought accolades. She never asked for praise from others, or she just wasn't the kind of person that we see all too often these days. She was the kind of person that more of us should aspire to be. Though in many regards it was a melancholy life. She never married. She never had children. She battled medical issues for much of her adult life. She lost her hearing at a young age. She didn't make much money. She lived alone. But for all the things that she didn't have, there was one thing that she did have that no one could take away from her. Not any person, not any sickness, not any disability, not even an unpaid internship for nearly a decade. Nothing could take away her love of astronomy and her joy and sense of pride that she found in her work. There's this poem that I read when I was a kid. I read it and I didn't understand it. I saw it again when I was 18 or 19 and I laughed at it. I saw it again when I was 25 and I didn't laugh again. Now at 41, I read it at least a couple of times every year to remind myself of what's really important in life and what path to keep when things get tough. Learning about Henrietta over these last few weeks, she reminded me of this poem. So I'd like to share it with you all. I promise it's not long. The name of it is Desiderata by Max Ehrmann, and I promise it's brief. Go placidly amid the noise and haste, and remember what peace there may be in silence. As far as possible, without surrender, be on good terms with all persons. Speak your truth quietly and clearly, and listen to others, even to the dull and the ignorant. They too have their story. Avoid loud and aggressive persons. They are vexatious to the spirit. If you compare yourself with others, you may become vain or bitter, for always there will be greater and lesser persons than yourself. Enjoy your achievements as well as your plans. Keep interested in your own career, however humble. It is a real possession in the changing fortunes of time. Exercise caution in business affairs, for the world is full of trickery. But let this not blind you to what virtue there is. Many persons strive for high ideals, and everywhere life is full of heroism. Be yourself. Especially do not feign affection. Neither be cynical about love, for in the face of all aridity and disenchantment, it is as perennial as the grass. Take kindly the counsel of years, gracefully surrendering the things of youth. Nurture strength of spirit to shield you in sudden misfortune. But do not distress yourself with dark imaginings. Many fears are born of fatigue and loneliness. Beyond a wholesome discipline, be gentle with yourself. You are a child of the universe, no less than the trees and the stars, and you have a right to be here. And whether or not it is clear to you, no doubt the universe is unfolding as it should. Therefore, be at peace with God, whatever you conceive him to be, and whatever your labors and aspirations and the noisy confusion of life, keep peace in your soul. With all its sham, drudgery, and broken dreams, it is still a beautiful world. Be cheerful. Strive to be happy. Epilogue. In the 1920s, astronomers all across Europe were abuzz, celebrating excitedly while beginning to cite and discuss Miss Leavitt's Law as a new foundational tool for measurements in astronomy. Leavitt had published her groundbreaking work on period luminosity relationship for Cepheids in the 1912 Harvard College Observatory Circular, which Harlow Shapley, as we learned earlier, then successfully used to begin mapping out the Milky Way. He wrote countless papers which were widely read internationally and always cited his friend and colleague Henrietta. Information traveled slower, though, in the 20s, and it wasn't until 1925 that one Gösta Mittag Leffler, who was at the time a huge figure in Swedish mathematics and indeed a massive advocate for women in science himself, had learned about Henrietta's massive contribution to science and the world, and he wanted to do something about it. Having the influence that he did, Leffler nominated Henrietta Swan Leavitt for the Nobel Prize in 1925, citing her period luminosity law as clearly being Nobel caliber. Leffler also had a very good track record of making sure women scientists got the respect and adoration that they deserved. Having never met Henrietta himself, He was beyond excited at the possibility of speaking and perhaps even presenting a Nobel Award to her in the near future. After poring over her work for weeks and realizing this uncelebrated hearing-impaired woman in Cambridge had certainly done what it takes to earn the respect and adoration of the entire scientific community, he nominated her. After leaving home at 17, battling countless obstacles, medical problems, financial issues, and everything else that she struggled through over 30 years, Henrietta Swan Leavitt had been nominated for a Nobel Prize. But as I said earlier, news traveled slower back then. Sadly, Loeffler had no way of knowing at the time, 4 years prior to his nomination, when all of Europe's astronomical community was celebrating her achievement, Henrietta Swan Leavitt had just passed away at the far too young age of 53 years old. She died of stomach cancer. The Nobel Committee, unfortunately, has always had a rule against awarding posthumously. So sadly, the nomination had to be withdrawn. Henrietta Swan Leavitt never sought fame, never chased fortune, and never clamored for recognition. She spent her life in quiet rooms, carefully looking over glass plates, listening, not with her ears, but with her eyes, to the faint, rhythmic pulsing of distant stars. In those flickering rhythms, she found a universal yardstick, one that would let future astronomers measure the cosmos itself. She never married, never had children. When asked her occupation, she simply said, "I am an astronomer." And though she died young, at just 53, her work has outlived her, echoing across the universe. A Nobel nomination came too late, arriving only years after her death, yet her law became the very foundation of much of modern astronomy. Her middle name was Swan, fitting then that what she left us was kind of a swan song, not a lament of endings, but a melody of beginnings, a song written in starlight and whispered through the Cepheids, carried across time and space. It's the music of distance made measurable, of the universe made knowable. Henrietta Swan Leavitt may have ended in 1921, but her swan song is still being sung every time we measure the distance to a star, a galaxy, or the very edge of the observable universe.
The Odyssey. I've accepted that I'm different. God bless me with the wisdom to see past the Jews and the cars and sex and women directly to the finish. You're obsessed with your image. I'm in it for the distance and I won't rest until I'm finished. Perfect your gimmicks. I make progress with every sentence while the underground patiently awaits my next visit. The best arisen from the depths of the ghetto in the system. Remember what you hear so you can tell it to your children. Trying to contain these aggressions that I'm feeling so I can sneak into the mainstream and spread it to a million. We all got something to say, but they never listen. That means the only way is to yell it and to spit it. The Odyssey. The Odyssey.
Time to sit back, reflect, converse, what's next, learn what's left as the story unfolds. We accomplish new goals, looking for loopholes. We resume alone on a level of...
A very special thank you to all of my Patreon supporters who have been supporting me for so long now. I would not be able to make this show without your support. If you would like to support the Astrocast, you can do it at patreon.com/the Astrocast. We hope to see you in our community Discord, but until then, as always, clear skies.
Patience as I converse my information. Having lots of dedication is my only explanation for the reason that I'm waiting for my chance to be heard. As I continue on my quest, I put my best in these words. I turn the Rubik's Cube again, but colors never really change. As I unravel life's mysteries, I reach a higher range. And to the people that are next to me and those I've left behind, I think about how much I've learned in such a short amount of time. In my past I don't regret, and to the cats that I have met, I hope you never do forget that I'm forever in your debt, because I wouldn't be me if it wasn't for these people that have impacted upon my life, both positive and evil. I continue through the struggle and I cipher through the rubble. I know I finally pierced the bubble, cause every year my knowledge doubles. The Odyssey, the Odyssey, the Odyssey.